Welcome back. We're just going to finish up genetics here in this last video. So far we've talked about Mendel's first and second laws, and then we talked about codominance and incomplete dominance. And we're going to finish up now by talking about genes which are sex-linked. So that means they're found on the X or the Y. And we're going to focus our discussions on genes which are linked to the X chromosome. So far, all the genes and the alleles we've talked about have been on the autosomes. The autosomes are the chromosomes which are not the sex chromosomes. So in humans, the sex chromosomes are X and Y. And so we're going to talk about genes and alleles present on the X chromosome. There are some genes present on the Y chromosome, but we're going to focus our discussion on genes which are found on the X chromosome. So, hopefully you remember from earlier classes that females have two X chromosomes and males have an X and a Y. And it's this observation that leads to some of the interesting phenomena that we'll take a look at. Now, we're going to investigate this using an example, and the classic example is hemophilia. Hemophilia is sex-linked, so you're going to find this more in men than you are in women. Just going to give you a quick introduction to hemophilia. This isn't too important in terms of the genetics, but it's just useful to know. Hemophilia is a blood clotting disorder, so hemophiliacs cannot clot their blood properly, and that is due to a genetic defect in the gene which produces a protein, a clotting factor in the blood called factor VIII. And if you don't produce factor VIII, or you produce a mutant form of factor VIII, then you cannot clot your blood. So there's a gene that produces factor VIII, and then there are two alleles of that gene. And those alleles are found on the X chromosome. Well, that gene is found on the X chromosome, I guess we should say. And so the two alleles are X superscript uppercase H and X superscript H dash uppercase A. We're going to call those XH and XHA. So those are the two alleles that we're going to be discussing. Let's take a look at the genetics very quickly. So let's imagine that we have the situation where we have a man who's got a normal XH allele. And so on his X chromosome, he's going to have an XH allele. Now, he's got a Y chromosome, so he doesn't have another allele of the hemophilia gene. And so in this state, we can't describe him as heterozygous or anything like that. We have to describe him as hemizygous. That means he's got half of the dosage of this gene. So the male is going to produce gametes which are either going to have the XH allele in them, and so one gamete, gametes can either have the X chromosome or they can have the Y chromosome. Now, let's consider a female who is a carrier of hemophilia. So that means she's got one normal, one wild type allele, X uppercase H, and she's got one mutant allele, one defective allele that doesn't produce factor VIII, so she is XHA. Now, the XH allele can produce enough factor VIII that she doesn't have any of the phenotype associated with the disease, so she's ostensibly normal. She would only be hemophiliac if she had two defective alleles. A male, on the other hand, because you've only got one X chromosome, if he's got the XHA allele, then he has no other X chromosome, so he can't have the normal allele, and so he can't be heterozygous. And so if he's got the XHA allele, then he's going to be a hemophiliac. So let's see what happens when we perform fertilization with these different gametes. So if we take the two XH gametes, so the normal gamete produced by the male that contains the X chromosome, and the gamete containing the XH allele from the female, we would get a normal female. That's the top left-hand box. And so both alleles in that individual will be XH. And so there's no chance that defective XHA allele can be passed on. If we take the Y containing gamete from the male and we combine that at fertilization with the XH, then we have a normal male, because the offspring would be XY, and that would be a male. Now, if we take the defective allele, XHA, from the female, so we take that gamete, and we combine that with an XH from the man, so we take the sperm that contains XH and we do a fertilization there, we're going to have what's called a carrier female again. So that's going to be the same genotype as the female we started with. So that individual will have an XH and an XHA. So she carries the defective allele and can pass it on to a child. But you're only ever going to see the disease phenotype if she has a child with a man who has XHA on his X chromosome. So What about if we take the XHA allele, or the HA allele from the female, and we combine it with the Y chromosome? Now in that case, we're going to get a male with hemophilia because the sperm from the man had the Y chromosome in it, and the egg from the female had the HA allele in it, and so there's no normal allele to compensate for the defective allele from the egg of the mother, and so the child would be XY, and so a boy, and because the child would have one defective allele HA, it's not compensated for by a normal XH allele, that child would be hemophiliac. So that's what happens when we see sex linkage, and it's a little bit different. We see some unusual ratios than we would do if we were looking at a genetic disorder or a trait which is passed on the autosomes. So that wraps it up for genetics, and that wraps us up for the semester. So hopefully I will see you around in some other classes. Bye for now.